COG and the weight COG and the load distribution. That's the first. And the second is talking about the crane stability. It's a different class. And then the third is basic rigging engineering. So let we start with I introduce myself. My name is Nelson. I graduated from Indonesia Civil Engineering Department in 2011, and I started my career as a lifting and not as a lifting engineer, as an engineer actually since 2011, and currently I working in Azerbaijan as a methods engineer. So as a methods engineer, we are responsible about the structural engineering and the lifting engineering as well, and also the SPMT. So we are responsible about all the operation of during the fabrication and the offshore operation. So yeah, that's a brief summary introduction from me. And yeah, in 2021, I get a lifting engineering certification from Lloyd's Maritime in UK. And currently, I also work as a co-founder for the FDP Consulting. We can start from the force mass center of gravity and load distribution. We all understand that the COG and understand the weight and the COG is the main information that should we have during the lifting and perform the lifting engineering. Actually, there are three main information that we should have. First is the weight, second is the COG, and the third is dimension. This is three main information that we should have when we're doing the lifting engineering. So, but the dimension we can easily get from the drawings like that, or we can directly measure it when the object is ready. But for the weight and the COG, it's a little bit tricky to find the information. Sometimes it's when we doing the project, when the project is running with the proper engineering, uh, the weight always controlled by some engineers like weight engineering, if you know. So we can just reverse to the report, and we can compare with our calculation. So every step, it's the weight and the COG always controlled by them. But for some items, we cannot get the information about that. So that's why we need to understand how actually we could uh, find the or calculate the weight and the COG with the proper understanding. So first we will talk about the units. There are two units that we known in the engineering. First, the scalar, and the second is vector. What's the difference between scalar and vector? Scalar units is a magnitude that only has quantity. So it's like a density, mass, length. They only have a quantity. There is no direction in there. And the second is the vector units. The the vector units is a quantities fully described by magnitude and direction. So it's like a force, velocity, like that. So the difference is only in the direction. The scalar units doesn't have a direction, and the vector units it has a direction. So this direction, the one which has direction like the vector units, we can combine it with, for example, one force uh, has the direction to this way, and then other force has a direction to this way. We can combine these two things, just like uh, to find the combined force direction like this. That's the difference between vector and scalar. And then the other basic things that we should know about the lifting is Newton's law. First, Newton's law is if an object is at rest and the forces that acting on it are balanced, and the object will remain at rest. However, if the object are moving on and the forces that acting on it are balanced, then the object remain will be moving with a constant speed. So if we have a object sitting on the, let's say it's no friction acting on the here, and there is a forces there are forces acting on the both side, and the forces are same. Then if this object is on the rest situation, then it will be remain rest. So it will be not moving because there is no uh, forces acting on the forces is are same. But if the forces the same situation, but the object is moving with the constant speed, then it will be remaining move but with constant speed. So there is no acceleration acting on the object. That's the first Newton's law. The second Newton's law is the acceleration of an object is dependent upon net force and mass. So this is the force equal to mass times acceleration. And the third Newton's law is if an object exerts a force on object B, then object B must exert a force of equal magnitude and opposite direction back on object A. It's So if there is two objects, let's say A and B, and this give a force F to the B, then the B will respond with the same force to the A. So it will equal the total force acting on the system will be zero. That's the third Newton's law. And then we will also talk about force and moment. Force is an influence that causes an object to change velocity or direction. That's happened because there is acceleration on this formula. Force equals mass times acceleration. And moment is a measure of the tendency of a force to rotate an object. So from here, we can understand that the moment will happen when the force has a distance to the center of the moment center. So it will be like this. We have a wrench right here, and then force acting at the edge of the wrench here, and there is distance to this is the center of the moment, and then there is distance to the moment to the center, and it will acting and the moment will be happen because there is a distance right here. And if we have a force angle like this, and the distance will become smaller in here, and will be the smaller moment will be happen to the at the center moment. But if the force exactly sitting on the center of the moment here, there will be no moment because the distance is zero to the center. That's the formula saying to us about the moment So there is correlation between force and moment. Uh, Moment happen because the force acting uh, because there is a distance between the force and the center moment. If there is no distance, then there is no moment, like this case. So yeah, that's the force and moment, and then we talk about mechanical statics equilibrium. So when we're doing the lifting engineering, the one the goals that we want to achieve during the lifting is the object that we lifted, it's on the equilibrium statics. It means it will be no there will be no additional force or moment acting during the lifting. So to get the lifted object in an equilibrium, we must fulfill this uh, formula in our analysis. So for example, when we have a hook right here, and then we have object here. If the COG is not in line with the COG, then there will be, let's say, E here. This object will move to get the equilibrium statics, to fulfill the equilibrium statics. How will it respond to the system? This COG will be shifted to make it in line with the hook. So it will be moved to here. But in order to move the COG to become in line with the hook, then this structure should be moved to here. Once the COG in line with the hook, that moment will lead to the system to the statics equilibrium, because this force the moment will be become zero, because there is no distance, there is no gap between the hook and the COG, and the force itself will be become zero, because this force acting on the object will be in line will be same with the hook here, uh here. So so sometimes people say that if there is the tilting on the object, it will be not a good lifting. Yeah, that's true. But sometimes we need to tilt this object during lifting to get the equilibrium fulfilled on the system. So that's how it works actually. For example, about this mechanical statics equilibrium, find the distance, and we have a system here. P1 is a 10 kilonewton and the P2 is a 20 kilonewton. Find the distance A and B to make this system is in equilibrium. So to make these things in equilibrium, we could we could find with the sigma moment equals zero. So for here, let's say, sorry. So here is, let's say, M1, and then here let's say it's M2. To fulfill the static equilibrium, there is a requirement total moment equals zero. So M1 should be equals to M2, and then P1 times A should be P2 times B, and then A equals P2 times B divided by P1. That's the first formula we have. And then if we use the total force equal zero, then the total force will be P1 plus P2 equals, there will be a reaction from here. Let's say P1 plus uh yeah, P1 plus P2 equals, let's say, P. That's the second we have. So, and then we also have A plus B e- equals 10. A plus B equals 10. And then B equals 10 minus A. This we can, so we back to the formula number one. A equal P2 times B divided by P1. P2 times 10 min A, like that. So we can get the A from this, right? P2 is 20. So A 200 minus 20A divided by 10. So it will be 3A 20. A equals 20 by 3. And then we can find the B by B equals 10 minus A, 10 minus 20 by 3. So if we apply this distance or dimension A20 by 3, and then here is 10 by 3, this system will be not moving because it's already achieved the static equilibrium. That's all. So that's what we want to achieve during the lifting operation. Now the how to composing of forces. There are two methods we usually use to combine the forces. First is a tail-to-tail method, and the second is head-to-tail method. The first tail-to-tail method, so if we have two forces acting in one object, F1 is a red and F2 is the blue, we can combine it by attach the tail from each forces here, and then by that we put the line, we take the line, same line as the each forces on the head, like this. This is what in line with the F2. This line is in line with the F2, and this line in line with the F1. The intersection between the imaginary line is the forces, combined forces. So that's the resultant. If the second one is a head to tail, so we combine the head of the same situation, the same sample, we combine it. So for example, the F2, we combined it. We put the tail of the F2 on the at the head of the F1 here. It will give the same result as the first one, but it depends on you which one will we choose to combine the forces. So we put the imaginary line that in line with the F2 here, and then in line with the F1 here. So the combined forces, the intersection will be here, and then we connect the tail of the F1 to the head of the F2 as a resultant of the forces, like that. It's easy. It's not really complicated actually. It's a from high school, if you notice about that. So basically the engineering, lifting engineering, if we back to the basic, it's coming from the high school formula, physics basic, if you notice about that. And then when we get the into the college, it's getting more detail. So the physics engineering will be learned very detailed in the college, but the basic is coming from the high school. So for example, we have two forces acting here. F1 is the red color, F2 is the blue color. It has the same direction to the x positive. F1 is 10 kilonewton, F2 is 8 kilonewton. To combine that, so we can easily just sum up both the forces. F1 plus F2 equals 18 kilonewton. So the direction will be uh, same as the F1 and F2, but it will be more longer because that's how vectors unit works. So the direction and the line is describe the units itself, or the quantity itself. The second example is the F1, the right one is 10 kilonewton, F2 is 8 kilonewton, but it has a different direction. The F1 is on X positive, but the F2 in the X negative. So we can get the resultant just uh, F resultant equals to F1 minus F2 equals 2 kilonewton, and the direction will be to the F1 because it's bigger than the F2. And then the third one is if the F1 10 kilonewton acting on the X positive and the F2 8 kilonewton is acting on the Y negative. So on this case, we need to use the trigonometry, I think. Yeah. So to get this, we can, we will know that the direction will be like this. And to get this, we know the trigonometry is, for example, this A and this B, then this C equals is square root of a square plus b square. So that will be lead to this. So resultant is a square root of 10 square plus 8 square. It's equals to 12.8 kilonewton, like that. And the direction will be this. And the fourth is we have three forces acting on the object. First, F1 is acting to the x positive. It's 10 kilonewton, and the F2 y negative is 8 kilonewton, and then F3 is 5 kilonewtons to the x negative. So to get this solved, then we need to fix it step by step. Step one, we need to fix this first. So FR1 equals to F1 minus F3 equals to 5 kilonewton. And the direction will be to this. FR1 equals to 5 kilonewton. And then we from FR1 and F2 we combine them together to get the FR2 or a resultant 2. That will be used the trigonometry FR1 square plus F2 square. So it will be square root 5 square plus x square. Wait. Five square plus 8.
6.2.
Yeah, it's 9.43. And the direction will be we will make imaginary line here, make imaginary line here, and then put the line here. This is the combined force from these three forces, like that. Is there any question from this? Any question?
Any
Still okay?
I think so. It's 6.2
okay.
kilonewtons.
Huh?
It's supposed to be 6.2 kilonewton.
5 square plus x square. No, it's 9.43.
Okay.
Is that right?
It's plus, right? Okay, fine.
Uh-huh. Because
Okay. Sorry,
yeah,
I did minus here. Okay.
yeah. Any question for this
Yeah, do you have any question? Because after that, the topic will be more complicated. Not difficult, but complicated. So before we will continue for the next topic, if you have any question here, you just feel free to ask. Aiman just joined with us. So welcome to Aiman. And then enjoy your learning session with us. So do you have any question?
no, we continue,
We'll continue.
right? So we continue with the weight calculation. It's not really complicated, but some of them is tricky one. So weight is important information to know before performing the lifting operation. Like I mentioned before, there are three main things that we should know before doing the lifting engineering. First is weight, second is COG, and the third is dimension. And the first main thing is weight that we should know. This information should be collected and known before the engineering design or the lifting operation itself. What is weight calculation? It's a process of calculating the total weight that can be lifted to ensure that all rigging and cranes are within the limits. So this is our basics to do the engineering. Why is it important? To prevent overloading, to make sure all personnel safe and more efficient. So when we know the weight itself, we can design the lifting arrangement with more efficient. Why? Because for example, we have a 10 tons structure to be lifted, right? We can easily use for example 10 tons cranes to lift the object. Is it safe? Yes, it is safe. But is it efficient? Well, that's we need to that's the problem. Is it efficient or not? Because there's so many perspective that can lead the answer to that. Is it efficient or not? So by knowing the weight itself, we can choose what equipment we need to do the lifting operation itself. Things that need to be considered in heavy lifting design. This is regarding the weight and COG. First, the object's weight. Second is rigging weight. Third is center of gravity, and the fourth is load distribution. In weight calculation, the formula that can be used is weight equals to mass times gravity, or 9.81 meter per second square. This is so this weight is a factor units, as we know before during the Newton's law. This one, the second Newton's law, saying F equals m times a, where a is acceleration and the gravity, it's considered as acceleration. So when we're talking about weight, it's always in Newton or kilonewton, basically. But sometimes in real life, it's mixing up everything. So like in the when we're doing operation, sometimes someone asking us about what is the weight, and we also always answer with the ton or kilogram, which is not correct. The correct one is we answer it with the Newton units or kilonewton, because that's the units for forces. But that's a common now, so yeah, we need to for me that's okay, because it's like we convert from ton to kilonewton, and easily for them to comparing with the catalog, which is usually is in ton or kilogram. But for reporting, I think it's not proper if we use weight units as a mass units. So we need to make it right. So if it's weight, then we need to mention that it's in Newton or kilonewton. Then, and in if it's mass, then we can use ton or kilogram, like that. Density is the mass of an object in 1 unit volume, kilogram per cube meter. So we need to know what before we calculate the weight, we need to know what is the material of the object. Like for example, if it's concrete, then the density will be 2.3 tons per meter cube. Asphalt concrete 2.4, bricks 1.9, cement 1.4. That's the important. So how to use the density to get the volume? This is the example. First, we have a steel block as shown with the width 0.1 meters, height 0.1 meters, and the length is 5 meters. First, we need to calculate the volume. Volume is section area times length. The section area is 0.1 times 0.1 times the length itself is, then the total will be 0.05 meters cube. And then after that we calculate the mass. Mass is volumes times density. The density is as we seen before for the steel it's 7,850 here kilogram per meter cube. So volume times density. Density is 7.85 tons per meters cube. Then we get the mass is 392.5 kilograms. And then after that, now we can calculate the weight. The weight itself is mass times gravity. 392.5 times 9.81 for the gravity, and we got 3,850.43 Newton for the weight. That's the sample number one. Sample number two, if we have a steel bar as shown, so the diameter is 1 meter and the length is 5 meters. First, same process as before. First, we need to calculate the volume, section area times length. Because the section is a circle, then we need to use the circle formula. And then we get the volume is 0.785 meters cube. Calculate the mass, volume times density. The density for the steel is as shown before is 7,850 kilogram per meter cube, and then we get the mass is 6,162.25 kilograms. And then after we get the mass, then we can calculate the weight. Weight is mass times gravity, and we get 60,451.67 Newton. Yes, Ahmed, any question?
Yeah, this I have just one concern. This weight of calculation means at the last acceleration, you calculate with acceleration, oh sorry, gravity,
Yeah.
9.81. Yeah, this is just for conversion of the conversion for kilonewton, right?
Yes.
All right.
So we should separate the mass and the weight. The mass is scalar units and the weight is vector units. So in our calculation for lifting engineering, we always use the weight. For example, like this, because weight is a vector units, then it says direction of the forces. For example, like this. If we have the steel bar like this, then this weight will be acting at the COG like this. from this, we can find the reaction at the lifting point. And the reaction itself is vector units. So this direction is that's all we need to get to design the lifting operation, like the rigging and the lifting attachment like that. So we should we should separate the mass and the weight. That's all. And for the lifting design, always use the weight because it's a scalar unit, vector units, and it has a direction on the forces. That's all. The third example, the other example is if we have a beam like this, how to calculate the weight of this beam? Then we need to. It's the same process as before. We just need to get the volume, mass, and then we can calculate the weight. But to get the volume, it's a bit tricky because there are 3 sections on here. It's not actually 3 sections. It's a 1 section. But to get the volume, to calculate the section area, I separate. Spread into 3 sections area. So the red one is area 1, and the gray one is area 2, and the yellow one is area 3, just to make it simple to calculate. Once I have 3 area here, then I can calculate the area per each area, per each section. So the width for area 1 is 100 here. The thickness is 18. 18 will be same here, also 18. And then the total area for area 1 is 1800 millimeter square. Same process with the area 2. I have the width here. It's 264, and then the thickness is 11, and then width times thickness, then I get the area is 2904, and then the area 3 also same, 300 times 18, 5400, and then the total area now is 10,104 millimeter square. It equals to 0.01 meter square. And then we can calculate the volume now. Section area times length. The length is mentioned here is 6 meters. So it will be 0.01 meter square times 6 meters. It will be 0.06 meter cube. And then after that, we calculate the mass, volume times density, because it's steel. Then we use 7,850 kilogram per meter cubes as a density. Volume is 0.06, then mass is 471 kilograms. After we get the mass, then we can continue with the weight. The weight is mass times gravity, 9.81 meter per second square. 471 times 9.81, then we get 4,620.51 Newton here for the weight. Is there any question with this weight calculation? I think that's all for the weight calculation. Is that's the basic that we can use for. But yeah, I think that's the basic. Any question for the weight calculation?
Any question? Any question for the weight calculation? Maybe from Jackson, from Jason, from Wallet, and from Aiman. Do you have any question before we continue for the next topic? So far,
Nothing from my side.
okay,
Yeah.
so far so good, yeah.
All right.
That is okay.
We continue with the COG calculation. Definition: the center of gravity is the point where the weight of the object acts. Why this is important? To get the first is to get the balanced lifting system. Second is to know the behavior of the object during lifting. For example, the load distribution and the object incline. If it's inclined, then etc. etc. And then the third one is to optimize the design since we know the load distribution, then we know where to put the lifting attachment and how to design the lifting attachment itself. Sometimes we use a pedi or a trunnion, and then we can also optimize the design of the rigging itself. For example, if the load distribution we get 50 kilonewton, then we can use the rigging maybe 70 kilonewton capacity like that. So for the for example, we have two objects here, and each of the object has their own COG, right? Now we want to lift these two objects together. Then where is the combined COG? That's our basis to design the lifting arrangement here, like that. Okay. So we cannot just use the blue object COG or the other one, but we need to combine the COG, and how to get the COG combined related to the our lifting design. That's before we get into the COG calculation. The main thing that we should know is about static determinate structure analysis. I hope you guys already known about this. So we have let's say we have a system like this. There is a member A to B with the total length of 10 meters. This A and B we can interpret as a lifting point, or uh, anything else. We can interpret as a support, like that. So we have a joint fixities A and B here, and the distance is 10 meters, and there is a member between A and B, and the load acting on the member is exactly at the center of the member. It's 20 newtons. So to get this, the first thing we need to find is what is fixity reaction. Fixity reaction is a reaction of the what you call it. Let's say this is the lifting point, right? The fixity reaction is a reaction at the lifting point because of this load or forces acting on this member. So to get the fixity reaction at joint A, for example, at joint A, then we should apply sigma moment equals 0. Anybody knows about this static determinant before? Or this is the first time to get these things?
Do you learn before about static determinate? Do you learn before, or this is first time for you to learn about this? So if this is first time for you to learn, we can explain more. But if you already get before from your college, for example, so it's more easy for you to understand. So
Yeah, for me, this is first time.
This is the first time, Ahmed.
This is first time. How about Jason, Jackson, and Ayman? This is first time.
Yeah, we have come across this in the college. Yeah. I have a fair idea what it is.
All right.
Yeah.
Okay. So
I also got learned before.
okay. So before we get into this, we have discussed about forces and moment, right? So moment is the where is this moment is forces times distance. Moment is a measure of the tendency of a force to rotate an object. So when there is a distance acting on the forces, then there there will be a moment. So that's why we will apply that to calculate the fixity reaction. So when where is the basic? So the statics equilibrium saying that the total forces equals zero, and the total moment equals zero. This will be used to get the fixity joint reaction. So when we saying that this system in the equilibrium, then we can apply that formula like total forces equals zero and the total moment equals zero to get the fixity reaction. So yeah, for example, fixity reaction at the joint A. So we want to know what is the reaction of at the joint A here. Then we can apply the total moment at B equals zero. Why? Because if we use the total, because there is no distance to the if we use total moment A equals zero, then this reaction at A have no distance to the joint itself. So we use the total moment at B equals zero here. So what is total moment at B equals zero? The the moment at B will be introduced by the reaction at A because it has distance to B here to 10 meters and 20 Newton forces because it has 5 meters distance to B. So total moment at B equals zero, it's a reaction at A times 10 meters minus 20 Newton times 5 meters this distance to B. So from that formula, we can get the reaction at A equals 10 Newton. And then for the reaction at B, to get the reaction at B, then we use total moment at A equals zero. And what moment acting on what forces acting that can causing moment at A, then there will be a reaction at B times 10 meters, the distance to the point A, and then there is 20 Newton times 5 meters. It's the distance to the point A. So from this formula, we can get the RB equals 10 Newton. And then once we get the reaction at A and reaction at B, then we can check the equilibrium. Total forces equals zero. the forces are A and then RB, because they have same direction, then it will be plus, and then minus 20 Newton because it's acting in a different direction. And reaction at A we get 10 Newton, and at B we get 10 Newton. 10 Newton plus 10 Newton is 20 Newton. 20 Newton minus 20 Newton is 0. Then we can conclude that the system is already in the equilibrium, like that. So the reaction at A is a 10 Newton, and then at B is a 10 Newton, like that. Any question, Ahmed? Is that clear for you?
Yeah, clear.
All right, perfect. And then we get into the case 2. So we have the same case, but the 20 Newton forces move 2 meters to join A. So the 20 Newton will be remaining 3 meters to the A, and then to B, it will be 7 meters. We want to get the joint reaction at A, then we use the total moment at B is 0. The moment at B, they are reaction at A times 10 meters, the distance to B, and minus 20 Newton times 7 meters, the distance to B. Then we get the reaction at joint A is 14 Newton. Same process we use to get the reaction at joint B, and the total moment A equals 0. Then the RB is 6 Newton. Once we get the reaction at joint A and B, then we can go into the equilibrium check just to make sure that our calculation error on the reaction is correct. Equilibrium check, total forces is 0, then RA plus RB minus 20 Newton. The RA we get the 14 Newton plus 6 Newton is 20 Newton, minus 20 Newton is 0. Then we are okay for that reaction. That's for the case 2. And then for the case 3, same situation, but the 20 Newton move 3 meters from the case 1. The case 1 is at the center, exactly at the center, 5 meters from A, 5 meters from B. Then for the case 3 is move 3 meters to the B, so it will be 8 meters from A, and the total length is 10 meters. And the forces acting still same, 20 newtons. We want to get the joint reaction at 8, then total moment at B is, we use total moment at B as 0. And then what's moment acting on B? It will be RA, or reaction at joint A, times 10 meters minus 20 newtons times 2 meters, 2 meters here. And then we get RA is 4 newtons. For the reaction at joint B, we use the same process. We use the total moment A equals 0. What is the moment at A? It's they are RB times 10 meters minus 20 Newton times 8 meters. So we get the RB is equal to 16 Newton. RA plus, and then we go to the equilibrium check. RA plus RB minus 20 Newton. RA we get the 4 newtons, RB is 16 newtons. It's so the total is 20 newton minus 20 newton. We got 0. Then we are in equilibrium right now. So that's for the case 3. Now the case 4, we get the distributed load here, length 4 meters, and the distributed load is a 10 newton per meter here. How to get the joint fixities reaction from this system? So first, we need to convert the distributed load becomes point load. So the total load is Q times the total length. So Q times L. It will be 10 times 4 meters. So the total point load that can be used is 40 Newton. And the COG, we can assume that it will be working at the center of the distributed load. But if it's a trapezoidal section, then it will be different. Okay, because it's so we can assume that it will be work at the center of the distributed load. Half of the length here is 2 meters from the each edge, like that. So now we can modify the system like this. This is W, the one we calculate the point load acting after we convert the distributed load. This is a 40 Newton now. And then now we can find it the reaction as a process, same process as previously. So to get the reaction at joint A, then we can use the total moment at P equals 0. Reaction at A RA times 10 meters. 10 meters is the distance A to B, minus 40 newtons times 4 meters. So the 4 meters is the distance from the COG to the joint B. So we get RA is 16 Newton, and then to get the joint reaction at B, then we can use the total moment A equals 0. Then what's the moment at acting on the joint A? There are RB times 10 meters minus 40 newtons times 6 meters. And then we get the RB is 24 newtons. And then we get the equilibrium check just to make sure that our calculation for the joint reaction is correct. Then RA plus RB minus Q times 4 meters. Q times 4 meters is W, the one we calculate before as a point load. RA is 16 Newton plus RB is 24 Newton, then it will be 40 Newton minus 40 Newton, then it will be 0, then our system is in equilibrium. That's all. That's for the case 4. And then the case 5, we have two different loads, P1 and P2. P1 is 10 newtons, and the distance 2 meters from A. And for the P2 is 20 Newton. It's 5 meters from A. The total A to B is 10 meters. Then how to find the joint reaction? First, actually we can calculate it by no need to calculate it separately. We just calculate it directly using the P1 and P2. But just to make sure that it's we understand how it works, then I will choose to calculate it separately. So first I will start with the P1 fixed reaction due to the P1 tenton. Find the joint reaction at A. Like the same process as before, total moment at B is equals 0. I will say for the case P1 equals 10 ton, I will say that the joint reaction is RA1 for the reaction at A and RB1 for reaction at B. So RA1 times 10 meters minus 10 newtons times minus 10 newtons times 8 meters. So we got RA1 equals 8 newton. So and for joint B, we use the total moment at A equals 0. Same process, then we got the RB1 is 2 newtons here. And then after that, we will continue with the case 2, that is because due to the P2 equals 20 newtons. We find the joint reaction at A, same process as previously, so nothing's new here. Joint reaction at A, use the total moment at P equals 0. Then we got the RA2 equals 10 newton, and then we find the reaction at B by using the total moment at A equals 0. Then we get the RB2 equals 10 newtons. After that, we get the total reaction. So the total reaction is at joint A is RA1 plus RA2, the one we calculated before. So for the RA1, for the reaction at A, we get 18 newtons. That's coming from the RA1, we got 8 newton and RA2, we got 10 newtons. So we got the total reaction at A, it's 18 newton. And then the total reaction at B is 12 newtons. And then we do the equilibrium check. RA plus RB minus P1 and then minus P2, because it's both of the forces has a different direction with the reaction. So 18 newton plus 12 newtons equals to 30 newtons. P1 minus 10 newton minus 20 newtons equals 0. So the system is already at the equilibrium. Yep, that's for the cases. Now the case 6. So we have P1 and P2. P1 10 newton, P2 20 newton, but the P1 it has a cantilever to the B. The distance is 2 meters here. So how to find the joint reaction? Same system. That there is no other formula to calculate the joint reaction, as long as static determinate. So to get the fixed reaction at joint A, then we can use the total moment B equals 0. What's the total moment? What is the moment acting on B? There is RA and P1. The RA is the distance to B is 10 meters, and the P1 the distance is 2 meters. The RA1 times 10 meters plus, why this is plus? Because it has same direction as the RA. So if the RA, the moment, because of the RA, like this, will rotate the member like this, then the P1 will make the moment to rotate like this direction. So it will be saying same direction of the moment. That's why we put plus here. So RA1 times 10 meters plus 10 newtons times 2 meters. So we got the RA1 equals to minus 2 newtons. If it's mentioned minus, then the reaction because of this P1, it will be like this. It will be on the different direction. And then to calculate the joint reaction at B, then the moment, we use the total moment at A equals 0. What is the moment acting on A? It will be RB times 10 meters here. And then there is 10 newtons times 12 meters. The distance to A, 10 plus 2 equals 12 meters. So we get RB1, 12 newtons. That's for the reaction due to P1. And then we calculate the reaction due to P2 equals 20 Newton here. The fixed reaction at joint A, then we calculate with the total moment at P equals 0. And then we got the RA2, 10 Newtons. And then fixed reaction at joint B, we use the total moment A equals 0, then we get the RB2 10 newtons. And then after we get the total the reaction because of the both forces, then we can easily just get the total reaction by combining all of them. So the total reaction at joint A RA equals to RA1 plus RA2. RA1 we get the minus 2 before, minus 2 RA2 we get 10 Newton. Then we get the total reaction for joint A is 8 Newtons. And then for the joint B, RB1 we get 12 Newtons. And then RB2 we get 10 Newtons. The total then 22 Newtons. And then we can do the equilibrium check just to make sure that the reaction that we calculated is already correct. Total forces is RA plus RB minus P1 minus P2 equals 0. RA we get the 8 Newton plus RB is 22 Newtons. If we total it, then 30 Newtons. And then minus 10 Newtons minus 20 newtons, and we got 0. Then we concluded that we have already the equilibrium. Is there any question for the joint reaction calculation before we get into the COG calculation? And I will explain why this reaction and how it works to the COG calculation.
Any question?
Is everything clear? I hope it's everything clear, yeah.
Yeah,
Jason, do you have any question or still okay?
I'm okay until now. Okay.
All right, perfect. Ahmed, you clear about this, Ahmed?
Ahmed, you clear?
Yes, I'm clear now.
All right, perfect, Ahmed.
Jason still working. His is under, yeah, still working. So Aiman text me still okay. Got learn from university. So we can continue.
All right, we continue with the COG calculation and find what is the relation with the joint reaction before. So to find the COG calculation, this is only the basics, yeah. So after this, we don't need to find the reaction to get the COG. So we just continue with the one single we just continue one single formula that we already got from the high school before. So we just want to explain how this formula we got, so it will be easier to us to understand how does it works, the formula itself, how it works. So yeah. So to find the COG calculation, for example, we have two forces acting on the system. Let's say it's a member A to B with a length of 10 meters. And the forces are P1 equals 10 Newton, and the second forces is 20 Newtons with this 2 meters from A for the P1 and 5 meters from the for the P2. To get to understand what is the combined COG is the combined COG is we we combine the P1 and the P2, but we don't know where is exactly the position, the location. The location of the combination of between P1 and P2, that is the combined COG. So P is the combination between P1 and P2. The location is unknown, and the location is, we called it COG. All right. So first, calculate the viscous reaction at joint A and B. This is only the basics, yeah. For the next, we can use that only use the formula. From case 5, joint reaction has been found as below. So this uh we got the reaction from the case 5. It's the same case as case 5. So for the reaction at A, we get the 18 Newton and RB is 12 Newtons. To find the COG location, so from the beginning we have said that the P is the combination between P1 and P2. So we can change the system become like this, which with a single load, which is P equals to P1 plus P2 equals to 30 newtons. But the location is unknown. I mentioned here is as X. So to get the to get the to get the X, then we can choose either is a moment A equals 0 or moment at P equals 0. For this case, I use the moment A equals 0. Then what is the moment at the acting at the joint A? There is RB times 10 meters minus P times X, the COG location, to joint A. P, and then from this we can get the P times X equals to RB times 10 meters. Then we get the X is 4 meters. So we can say that the COG is located 4 meters from A, like that. So this is the COG. So if we use this system to calculate the reaction, it will be going, it will, we will get the same reaction as this, like that. Another example is like this. So we have this is the same case as case 6, I think. So we got the reaction is at A we got 8 Newton, and at B we got the 22 Newton. And then we change the P1 and P2 as a single forces acting on the system, like this. to get the COG, let's say it's x1 from A or x2 from B, we can choose either it's a total moment at A equals 0 or total moment at B equals 0. For this case, I use a total moment at A equals 0. Then what is the moment acting at A? There will be P itself times x1, and we get the RB at times 10 meters, right? So RB times 10 meters minus P times x1. Then we get the x1 is 7.33 meters. So we got the COG or the P location 7.33 meters from the A. So it will be here, 7.33, like that. So now we can conclude that to find the COG, we can simplify by using equation below. This is what the formula I said before. So let's say we have a case like this. P1, we have two forces acting on the system, P1 and P2. The P1 is a x1 from A and the P2 is x2 from A. The total length is x. Then by assuming A is the origin point, then the fixed reaction at B is, then we get RB is RB is a P1 times x1 plus P2 times x2 divided by x, the total length. This is if we use total moment at A equals 0, then the RB times x minus P1 times x1 minus P2 times x2. Then we got this RB equals P1 times x1 plus P2 times x2 divided by the total length x. And then we convert or we change the load by combining this P1 and P2 becomes P here, which is the location is x3. X3 is the COG location or the combined load location. So the COG is x3, then we get the, if with the same origin point, fixed reaction at B is RB. So the total moment at A equals 0, then RB times x minus P times x3, the distance to A. Then we get the x3 equals to RB times x divided by P. What is RB? We get the RB here, and then we put here, and then P1 times x1, P1 times x1 plus P2 times x2 divided by x. We remove the x, so we get the, with this, so we have remaining P1 times x1 plus P2 times x2 divided by the total load. That's the formula that we can use to calculate the COG for all cases. That's all. So if we have another P3 here, for example, then we can use we can add another P3 here, P3 times x3 here. If we have four forces, then we can add another forces P4 times x4, like that. As long the concern the one need to understand here is we need to clarify the where is the origin point, and we need to uh, stick to use the origin point to calculate this distance like that. Is there any question for the COG calculation? Any
Any question,
question?
everyone? Do you have
Is
any?
it?
This if for P1, P2, P3,
Yeah.
imagine P3 is heavier and P2 is less heavier, then the COG
Mm-hmm.
will be more on the on the B side. So it does not matter like that.
Yeah, that will be this formula will be leading to that conclusion. So if the P3 is heavier than this P1 and P2, then the COG will be close to the P3. This formula will lead us to get the COG close to the P3 like that. You got my point, Jason.
Okay. Okay, for that reason. Okay.
Is that okay, Jason?
Yeah, fine.
Yeah.
Fine.
Any other question?
Any other question?
I got one question.
Yeah.
So
I'm working for Mammoth Malaysia because you not yet introduce yourself, Aiman. So I just quick introduce about yourself. Go ahead with your question.
okay. So actually, in the reality,
Yeah.
this P1, P2, is it the external force? Where does it come from?
Yeah, it's external forces acting on the system. So we have, for example, we have because this is a we start with the line with one single member, right? After this, we will continue with the two-dimensional. So I hope it will be easier to us to understand how this formula works. So for example, we have let's say it's a member, one single member, right? And then we get the on the top of the member we have different loads here, P1 for example, and then P2, and then we want to lift it. We want to design something. We want to design uh the lifting arrangement for this. So in order to design the lifting arrangement, we need to find the COG combined because of the P1 and P2, right? So to get the COG that will be used for the lifting arrangement design, we can use this formula. So the P1 and P2 is the external forces that will be acting on the system. It will be the same as if we have for example, if we have like this, so, right? Sorry, we have section like this. Then we want to lift it to here, right? We have a lifting point here and here. So if you want to find the COG by using this, then we can easily we can separate the section to two section. For example, the COG here and the COG will be here, right? So we can simplify the system will be like this. So this COG will be working at here, and then this COG will be working at here. And we can say this as P1 and this is as P2, right? And it has their own distance to our origin point, x1 and x2. Then we can use this formula to get the COG. Let's say after we use this formula, the COG will be here. So this system will be, the COG will be something around here. This is the already two-dimensional, but let's say to simplify, we use a single line system. So yeah, we will use we can use this formula. Either is external force or internal forces, like that, Ayman.
Oh,
Is that
okay.
is that clear for you?
Yeah, clear, sir. Thank you.
Yeah, thank you. Any other question? Is that or everything clear? Yeah.
I think so. I think so is clear, right?
Yeah, that's clear.
It's
All
clear, yeah?
right. Okay, let's continue with the two-dimensional COG. All right, there you go. Two-dimensional wake and COG. So the first one we have clear with the one-line system. Then we continue with the two-dimensional wake and COG. So let's continue with the case one. Case one wake. We have a steel plate 10 millimeter thickness as shown below. So this is the section. We got 7 meters at the top, 6 meters width at the bottom, and the total height is 10 meters, and the thickness is 10 millimeters. We want to calculate the weight and COG calculation. So to define, first we need to define the origin point. As I mentioned before, we need to the first thing we need to do is define the origin point and consistent to use the origin point as a distance to the each loads. First, we need to define the origin point. For this case, I will put the origin. It's free to you to put the origin point. So you can choose, maybe you like to put that on here or wherever you want. So for this case, I will put the origin point it's here, right? The second is divide into several parts. So for this case, I will divide it into 3 areas. The red one is area 1, is at the top here. It will be 7 meters times 2 meters. The area 2 is the green one, is 2 meters times 3 meters, 2 meters times 3 meters, and area 3 is the yellow colors, 6 meters times 5 meters. Right? And also it's free to you to choose whatever you want to be the area. You can choose, maybe you like to put like this. So this is area 1, 2, 3, or anything else. So it's free to you. So yeah. And the third one, calculate the weight of each parts and define their COG. For the area one, I will uh, the COG, we can say that it will be on the center because it's symmetrical. So 7 meter wide, 2 meters height. Then the COG will be at the center, 3.5 from the edge, each edge, and 1 meters height. COG location. First, calculate the volume, length time width times the thickness, 7 times 2 times 0.01 meters for the thickness. Then we get the volume is a 0.14 meter cube. And then the mass is volume times density, 4 meter cube, and the density, because it's a steel, then we get 7,850 kilograms per meter cubes. Then we get the mass is 1,099 kilograms. And then we continue with the weight calculation, mass times gravity. The gravity is 9.81 meters per second square. So we get the weight is 10,781.2 newtons. And then continue with the area 2. Area 2 is a green one, yeah. The green color is 2 meters times 3 meters. We check the volume. The volume is 2 meters times 3 meters times 0.01 meters for the thickness. Then we get the volume is 0.06 meters cube. And then the mass, volume time density, we get 471 kilograms. And then we continue with the weight. Weight is mass times gravity. We got 4,620.5 newtons. That's for area 2. And then we continue with the area 3. COG is still same because it's symmetrical. We can assume that it will be at the center. So for area 3, we get the volume is a 0.3 meter cube. And the mass is volume times density. We get 2,355 kilograms, and then the weight is mass times gravity. We get 23,102.6 Newton. Now we can combine all of them, area 1, area 2, area 3. To combine that, for the total weight, we can just total the weight for each area. So weight 1 plus weight 2 plus weight 3, we get the total weight is 38,504.3 newtons. And then to combine the COG, we use the same as previous, as I mentioned before, the formula. For the COGX, we can get we can use the formula by introduce the coordinate x here. So previously the formula is p1 plus times x1 plus p2 times x2 plus how many loads you have on the systems, and then divided by the total load, right? So for the COGX, then we use the coordinate x on here. To get the COGY, we use coordinate y on here. That's the difference. But the formula we will use the same. So for the coordinate x, we use the coordinate x. The weight of area 1 here, COG1, the coordinate, the x coordinate is 3.5. For the area 2 here, the x coordinate is 1 meters. For area 3 here, the coordinate is 3 meters. So we use the formula. The formula will be like 10,700 1.2. This is the weight of the area 1 here, times 3.5 plus 4,620.5, the weight of area 2, times 1 meter here, plus 23,102.6 weight of the area 3, times 3 meters here, and then divided by the total weight here. And then we get the COGX for coordinate x is 2.9 meters, like that. For the COGY, maybe you can, anybody else can help me to find the coordinate y. Maybe you can check calculate it by yourself for the coordinate y of the COG.
We try to give some exercise, right? Like a small exercise to make sure that our participant follow the courses well. So anybody can help Nelson to calculate this case. Jason maybe, or Ayman, or Ahmed.
Yeah, calculating.
I got the answer is 4.8 meter. Or what?
4.8. Let's see. Any get the different numbers? Anyone?
6.8. Let me cross check.
6.8. Six point eight. Okay, let's see what's the answer here.
Okay, I think so. It's not 6.8. COG3 is W3. Yeah? Okay, vice versa then. Okay,
Yeah, so we get
okay.
4.8 meters
4.8. Yeah.
from the origin point. So yeah, we use the same formula to calculate the COG both direction x and y. The only difference is if we want to calculate the COG for the x direction, we use the x coordinates for each COG. And if we want to get the COGY, then we use the y coordinates of each COGs. So yeah, that's the basics, but the formula remaining same. So, and then we continue with the case 2. So we have a deck platform here, 10 meters times 10 meters, 10 meters width and 10 meters length. Total weight is 300 kilonewtons. COG as shown in sketch here, right? 3 meters X, 4 meters Y. Will be lifted with one item uninstalled as shown in red. So this item in red will be not uninstalled. Calculate the lifted weight and find the COG. All right, for this, we need to define the origin point. The origin point, I will assume that it will be on here. Not assume, but I will put the COG on here, right? And then after we define the origin point, we define the COG of each items. As mentioned in the beginning, the COG platform is the total. It means the total of the platform, including the uninstalled item. It will be 3 meters X and 2.5 meters Y. For the COG of the uninstall, we can assume that it will be at the center because it's a symmetrical section. It will be 5.5 from the origin point for X and 4 meters from the origin point for the Y coordinates, right? After we get the COG of each items, then we continue with the combined weight and COG. Before it is said that the total weight of the platform is 300 kilonewtons. And then from the 300 kilonewtons, it will be taken the uninstalled item 80 kilonewton. So the remaining weight will be 220 kilonewtons here, right? To get the coordinate x of the combined COG, then it will be same formula. No, nothing's new. So weight of the total platform, weight 1, 300 kilonewtons times x1, the COG item 1. Let's say the total platform is item 1, and then the uninstalled item is the item 2. All right. So weight of item 1 is 300 kilonewtons, and times coordinate x of COG items 1 is 3 meters here. We use minus here because it's we need to take out the uninstalled item from the total weight. So we use minus here, minus of weight item 2. It's the uninstalled item, 80 kilonewtons times 5.5 meters here. The COGX of the uninstalled item from the origin point. And then we divide it by the total weight, 220 kilonewtons. So we get the COGX is 2.09 meters, like that. And then for the COGY, maybe you can check by yourself with your calculation with the same process, the same formula. Just need to change the coordinate. This coordinate x become coordinate y.
Any question? from all of you?
No, they are calculating
Sorry.
the coordinate for y.
4.5.
4.5. 4.5. Anyone gets a different number?
I got same 4.55.
4.55. All right. So for the coordinate y is we just change the x become y coordinate. So 300 times 4 meters for the COG platform minus 80 times 2.5 for the uninstalled item divided by 220 kilonewtons for the total weight. Then we get the COGY is 4.55 meters. All right. That's for the case 2. We continue with the case 3. Same deck, 10 meters times 10 meters, total weight is 300 kilonewtons. COG as shown will be lifted, include the scaffolding, 80 kilonewton weight. Location is shown in here, yellow color. Calculate combined weight and COG. So first, we need to define the origin point. I keep using this origin point here. And then divide the scaffolding area into several parts. So I will divide it into two sections. First, scaffolding 1 here, and then scaffolding 2 here. And then we calculate the scaffolding weight per area. First, we need to calculate this area distributed load of scaffolding. The first is the total weight, as mentioned before, is 80 kilonewton, and the total area is 51 meters square. Yeah, so the 51 is I got from 3 meters times 7. This is 7 meters. So it will be 21 square meter. And then 10 meters times 3 meters is 30 square meter. The total area for the scaffolding will be 51 square meter. So the total weight is 80 kilonewton divided by 51 square meter. It will be 1.57 kilonewton per square meter. That's for the area distributed load for the scaffolding. And then to get the weight of the scaffolding area 1, then we can easily use the area distributed load times the area, the total area 1. So the total area 1 is 10 meters times 3 meters, 10 meters times 3 meters, and the QS or area distributed load is 1.57 kilonewton per square meter. So the weight of scaffolding area 1 will be 47.1 kilonewton. And the COG, we can assume that it will be at the center because it's symmetrical, like that. For scaffolding 2, same. We can, for the weight, it's we can use the area distributed load times area 2. And the area 2 is 3 meters times 7 meters. The QS is 1.57. Then we get the weight of scaffolding for area 2 is 32.9 kilonewton. Like that. That's for the scaffolding 2. And then we continue with to combine with the weight and COG. The total weight, we can easily just sum up them all the item. So weight of item one is it's COG, the platform itself. Item two is scaffolding. Item one is a scaffolding one. Item two is a scaffolding two, and item three is a platform itself. So we total the weight, we get 380 kilonewtons for the total. For the coordinate x of the COG, then we can easily use the same formula. Weight of item one is here. The COG is here. The coordinate x is 5 meters. Weight of item 2, the COG will be here. It's 8.5 meters x. And then the item 3 is 3 meters x. Then divided by the total weight, 380 kilonewtons. Then we get the 3.7 meters for the COGX. And then we continue with the COGY. We just change the coordinate x become coordinate y. So we get the 47.1 kilonewton of weight of item 1 here, and the coordinate y is 8.5 meters plus 32.9 kilonewtons times 3.5 meters. 3.5 is this COGY of COGY of the item 2, and then 300 times 4 meters. 4 meters is this, and then divided by 380, the total weight. Then we get the COGY is 4.5 meters, like that. So for the COG calculation, is there any question, or maybe you have cases that maybe related to the COG?
Yeah, do you have any question or do you have any case from your side related with this lesson and you wanna share with us? Feel free to share with us.
I've got one question.
Yeah.
Now, in this figure, let us assume that the scaffolding area is a pipe spool. Okay.
Mhm.
Okay, and the pipe spool, and basically, in case if I want to find the of similar size, maybe a 10 meter by and 10 meter by 10 meter,
Mhm.
and in case the COG area, I assume it as a blank with zero weight, and use a similar formula?
Sorry. So you are saying that you have cases like this, 10 meters times 10 meters, and then you have a scaffolding on the
Now I'm
uh,
assuming a scaffolding area, the orange colored area is a pipe spool.
pipe spool, yes.
Yeah, okay. And imagine if I want to take the COG of that particular pipe spool,
Okay.
can I can go with a similar this analysis
Yeah,
where
it's the same.
COG platform will be considered as zero weight. Am I
COG
right?
platform. COG platform is
Yeah,
no,
because that's the blank area.
no, it's a COG platform. So the thing is the thing here is so you have a platform 10 meters times 10 meters.
No,
So
no, there is no platform actually. I'm talking about
oh,
lifting only a pipe spool. A pipe
okay.
spool, okay. And the shape of the pipe spool is similar to the scaffolding.
Okay, yeah, you can. Yes.
Okay, okay,
Just
yeah,
just take out the total weight of the platform and the
yeah,
COG, just blanket. Yeah.
yeah. Okay.
Yeah.
Thank you.
No problem. Is there any question? So we already done with the COG calculation, so we will continue with the lifting point reaction for the for the cases like this. So there are 4 points lifting point that we need to find, but this calculation is only works for a rigid structure. So for example, like equipment or a machinery like that. Once we get the non-rigid structure to get the lifting point reaction on a non-rigid structure, it will be considered as a indeterminate structure, which is we need to introduce the deflection or elasticity of the structure itself to get the lifting point reaction. So this methodology is only for a rigid structure. That's all. All right. So for example, we have a deck size 10 meters times 10 meters, total weight 300 as shown below this. I think this is the case we get from case 2, case 3, which is having scaffolding 80 kilonewton on the top and then will be lifted and then we need to find the lifting point reaction at A, B, C, and D by assuming the structure is rigid. So if it's not rigid, then you need to go to your structural engineers. They have ability to check the lifting point reaction by introduce the deflection and the material properties to the lifting point reaction calculation. So we assume for this structure is rigid. Let's say it's like equipment, machinery like that. From case 3, the combined COG has been found as shown below, 3.7 X and 4.5 Y. And then we distribute the load to a pair of sides and calculate the reaction. For this case, we can choose either it's to this side or to this side, right? So for this case, I will choose to this side. So, and then if I look at this direction, then it will be like this. The A and D will be at the left side and the BC will be at the right side. So the AD will be, the load will itself, it will be 3.7 meters from the AD and the total width, the total length will be 10 meters. From this, we can calculate easily with the reaction of AD and BC. AD is a reaction at A plus reaction at D, and while BC is a reaction at B plus reaction at C. Once we get the reaction on these AD and BC, for example, we get the AD reaction. This is the same the same process as previous, yeah. To get the reaction at AD, then we can use the moment at BC equals 0. So we get our reaction at AD is 239.4 kilonewton. And then if we want to get the reaction at BC, and this is BC, Then we use the total moment at AD equals 0. So we get the reaction at BC equals to 140.6 kilonewton. Then we do the equilibrium check, RAD plus RBC minus P. Then, and we get 0, then the system is already in equilibrium. And then once we get the reaction at AD and reaction at BC, then we continue with the to distribute the reaction to the H points. For the reaction AD, we use that for to get the reaction at A and D. For the reaction BC, we use that for the to get the reaction at B and C, like that. So if we back to this, first we distribute the reaction to here, right? Once we get the reaction, it will be sitting on here. And then we continue with the distribute the load to here and to here, to here and to here. Right? So if we look at here, this direction, then it will be A at the left and G at the right. And the load will be sitting on here, which is 4.5 from A, and the rest is to D, like that. And this load will be RAD. And if it's if we want to distribute to get the reaction at BC, then we use the reaction from RBC, like that. So RAD, we get the 239.4 kilonewtons, and the distance is 4.5 meters from A, and the total length is 10 meters. To get the reaction at T, then we use the total moment at A is 0. RD times 10 meters minus P times 4.5. And then we get the RD is a 107.73 kilonewtons. The same process we get we use for to get the RA. Is we get the 131.67. And then we use the RBC to get the reaction at B and C. So previously we get the RBC is a 140.6. Then it's located at the 4.5 from B, and the total length is 4 meters. Then the RBC, the RC equals total moment at B equals 0, then RC times 10 meters minus P times 4.5, then we get the RC is 63.27 kilonewton. And then for the RB, we get the 77.33 kilonewtons, like that. Yeah, that's all for the joint reaction calculation. So this calculation we usually use for this will be helpful for to find the lifting, not lifting, the to find the outrigger forces for the mobile crane. So we assume the cranes are a rigid structure, so there is no deflection introduced to get the lifting to the outrigger forces. So yeah, so we get from the catalog we can find what is the weight of the boom, the counterweight, the car body, or the it, the auxiliaries if any, and then the COG location we can assume we need to find it we need to find it the information from the catalog also, but if it will be better if it's very detailed information, and then we combine all the weight and the COG of each parts, and once we got the COG during the lifting, then we can use this methodology to get the outrigger forces of each supports like that. Is there any question for with regards to this COG and load distribution for two-dimensional object? After this, tomorrow we will continue with the three-dimensional object. So make sure that I just want to make sure that this two-dimensional has been clear, that you've got the an understanding by you, because the three-dimensional calculation, it will we will use the same formula, but I think it will be more detailed, but it will be stay the same, will be use the same formula like the previous one, this one.
For this, excuse me, for
Yeah.
the two-dimensional weight at A and D, the P is 239.4 and other one is 140.6. How exactly did we get that? Can you just come to that section? I just lost my concentration. Yeah.
The Okay. The You mean the 4.5
Yeah.
and for this 3.7, right? So
Yeah, yeah.
we get that from this. So when we first we like I said before, we can choose either it will be distribute to this side first,
Yes.
or to
Yeah.
this side, right?
Okay.
So for this case, I choose to use this side first, right?
Okay.
Okay, to get
Okay.
this side, then I will choose to see this side. So
Mm.
because we distribute to this
Okay.
side, then this load will be sitting on here and here, right? So
Oh,
if
yeah,
you
right.
if I look to this side, to this direction, then it will be like this.
Mm.
A plus D is this side, will be at the left, and
Yeah.
this side B plus C will be at the right side,
Yeah.
and the load will be sitting exactly at the COG at X direction,
Mm.
3.7, right? So
Okay.
for the 4.5, because it's already the distributed load
I
already
got it. Yeah.
sitting
Okay.
here, and then
Yeah.
we
Yeah. Yeah.
see this side like that.
Okay. 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 Clear. Clear. Okay.
Yeah. Anything else? Any question about this? Is everything clear right now? I hope everything is clear. Yeah.
Yeah. Almost got a vague idea. Yeah. Okay.
Okay. Perfect, Jason.
Ahmed, It's clear, Ahmed, Jackson, Ayman?
I think Ahmed has a problem with the network.
I think so. So, yeah, network issue.
So yeah, that's
Yeah,
for the TD mentioned.
driving back home. Okay, no problems. I hope tomorrow Ahmed and Ayman can join with us, full join with us. If they have any question, they can feel free to text. And during capstone project, you will learn more also, because your capstone project will comprehensive questions start from day 1 and day 2, and then it will be take a lot of value for all of you. So any question? This is the last.
And yeah,
Yeah.
Yeah, Jason.
no, nothing from myself. I believe I'm the only one left out.
Yeah, Jackson may be also still working now.
Okay.
I hope tomorrow.
So the one I just want to say that this once this program finishes, is that it doesn't mean that we already done. So if you have any cases out there, or you have cases with your project, you can come back to us, and maybe you need second opinion like that. You can ask us with your cases like that, so we can discuss more about that like that.
Yeah, sure. Yeah, I appreciate it. Yeah.
Yeah,
Thank you.
no problem.
So last slide this, or do we have still?
Yeah, this is the last. Yeah,
So
and tomorrow we continue.
tomorrow we'll continue with the same time, and then 30 minutes before I will open our Zoom so you can join. Why we open 30 minutes before we start? So I still have time to text all of you, and then you can join. So you can join when I said that 30 minutes our Zoom open. You can join, and I will text the other person that not yet joined with us. So that's why I need like 30 minutes before I will open our Zoom. Is there
Okay. Copy that.
is there any question?
No, nothing from my end. Thank you.
So
Yeah.
if there is no more question, I think that we can finish our class today. And maybe you can explain a little bit about first, or later on, or tomorrow. Yeah,
Tomorrow.
tomorrow we will explain about our capstone project. So tomorrow we will explain a little bit, so all of participants will join with us, and you will get good insight about that. So thank you so much, Jason, Jackson, and also Ahmed and Ayman. I hope you enjoy our class today. This is our first batch in English. Since first class, we will do our best, and I hope you enjoy and understand very well and get some knowledge about this. And see you tomorrow with the same time, and 30 minutes before we open our Zoom.
Thank you. Appreciate your time.
So much.
Yep.
Thank you so much.
Thank you.
Thank you.
See you tomorrow.
See you
Thank you
tomorrow.
so much,
You.
Bang Nelson. See you
Thank you.
tomorrow also. Okay.
Thank you.